Okay, so welcome everybody to the International Seminar on Automorphic Forms. Today we have Ameya Pitale from the University of Oklahoma that will teach us about the lifting of Maass forms to O1, 8n+1 and applications to the sup-norm problem.
Thank you very much. It's great to be here to give this talk. Thanks for giving me the opportunity. I wanted to give you some idea about some recent work that I've been doing. This is related to some liftings of Maass forms that I did with Yinkun, and then further investigations about those things, leading to some interesting applications to the sup-norm problem. So in this talk, actually, I just want to give you a flavor of the questions that we are trying to address, maybe a little bit of incomplete history, and then an idea of what kind of results you can obtain, and maybe a feeling for the proof and the methods. So let me, I have the chat window open down here. So if you have any questions at any point, please feel free to write in the chat window. I'll try to answer them. Also, you can see it's just 13 slides, or rather only 12 slides. So it's a very relaxed talk. So if you want to interrupt and ask questions, I'm very happy to do that as well. So let me start with some very general ideas about the sup-norm problem. I want to warn you a little bit. I'm not an expert in sup-norm problem, so the idea I'll give will be incomplete, so will the history. But hopefully it will convey the main thing that is going on. So so the idea is that you take maybe X Riemannian manifold and a Laplacian delta on X, and you want to, a natural question is to look at the L2 eigenfunctions of delta and study various different properties. So of course, there is a whole plethora of properties that you can focus on, and one of them is the sup norm. So we want to know something about the upper and lower bounds for the sup norm of this thing. Of course, if your manifold is compact, then this always exists. If it is not compact, then you put extra conditions so that the sup norm does exist. And to give you a flavor of how these sup norms show up, there is a very nice result of Sarnak, which says that if you are in the compact situation, and for an eigenvalue lambda, if V lambda is the eigenspace, then the dimension of the eigenspace is bounded by the sup norm. So the size of the eigenfunctions determine the size of the eigenspace. Not determine, at least bound it. So it's a very nice connection which tells you that the sup norm properties could give you relevant information about various different things. Instead of compact X, if you look at the arithmetic setting, which we will focus on quite a bit, then it has interesting connection to subconvexity bounds of L functions and so on. We'll not be going into these connections, but they exist, and we know subconvexity of L functions is a very hot topic. So that is another connection. So I want to give you some history, a very selective history, and to give you a flavor of what kind of results are out there. So I want to start with a result in 89 by Seeger and Soggy, and this is for compact X, where the dimension is 2, and they showed that the sup norm is bounded by the eigenvalue to the quarter. And you can see I'm dividing out by the L2 norm, because if you're talking about sup norm of an eigenfunction, you need to normalize it in some way. Because you multiply this eigenfunction by a constant, it's still an eigenfunction, but now the sup norm changed. So one of the ways you can normalize it is, well, you divide out by the L2 norm, and now the left-hand side is invariant under multiplying by constants. So you will see this ratio all the time instead of just the sup norm. So Seeger and Soggy said, well, it is lambda to the quarter for compact. And later, Sarnak extended this to higher dimensions. And he said, well, you can have a dimension up here. And if you additionally assume that phi is not just an eigenfunction of the Laplacian, but the entire space of invariant differential operators, then you can do better. You can have this rank X as well. In the case of dimension X equals 2, this is like 2 minus 1 divided by 4, which is this thing right here. So this is for compact manifolds. And in a way, if you are looking at the full generality, this is the best you can do. For example, you can look at the sphere, and then there are eigenfunctions which actually achieve this kind of a bound. So you really can't do better unless you look at either special classes of manifolds, or you extend to non-compact situation. The first results in that direction was again due to Sarnak. You'll see Sarnak's name a lot in the beginning, and that usually means that this topic in analytic number theory is becoming very famous because Sarnak is interested in it. And indeed, he did a lot of very interesting results to kickstart the whole project. So one of the results that Sarnak and Ivanich, they looked at the special case of X where H1 is the complex upper half plane. So either your gamma is coming from quaternions, so H1 mod gamma is compact, or your gamma is SL2Z. In either cases, Ivanich and Sarnak were able to use some additional methods compared to these earlier results, and they got an improved upper bound. You can see 5/24 is better than 1/4. And interestingly, they also got a lower bound, which is kind of significant because this says that if you look at all the eigenfunctions for all the eigenvalues, there is no uniform bound on the sup-norms. As the eigenvalue increases, the sup-norm increases too. So this lower bound is also quite significant. And so this was one of the landmark results which kickstarted lots of studies on these sup-norm bounds, saying that, okay, either if we are in the compact situation, let us try to break the bound which is coming from this result of Sarnak, or if you are in the non-compact situation, what can you do? Can you get the compact bound when restricted to compact sets, or can you do better? So these are kind of the questions that were being asked. And I want to kind of focus on 3 results in this direction. And all these 3 results were obtained in the context of modular forms using their explicit Fourier expansion, so a Fourier expansion method. So the first result was due to Xia. The first result I want to tell you is about Xia, and this is for holomorphic modular forms. And in this case, he got this amazing result where the upper bound is k to the quarter. You should remember that the Laplace eigenvalue lambda in the case of a weight k modular form is to the order of k squared. So this is really beating this lambda to the quarter quite substantially. And the reason that it does so well is when you look at the Fourier expansion of a holomorphic modular form, you use the Ramanujan bound for the Fourier coefficients, and the exponential function right next to it has super convergence properties. So together it gives you a very, very nice bound, which looks something like this. And this is kind of the best you can do in this case. Xia's paper is very accessible. If you get a chance to look at it, it's like 3 pages, beautiful result. That was my first paper that I read. Somebody who works in sup-norms told me, look at Xia's paper. This is the best way to enter into this area because it's very clearly written and it's a very nice result. So this was for holomorphic modular forms. If you want to look at Maass forms, then Templier was working on Maass forms in this case. And I want to give one of Templier's result written in the following form. So instead of the sup-norm in the numerator, I just want to take absolute value of f at any point in the complex upper half plane, because on the right-hand side, I want to give you a bound in where the y appears as well. And you can see if y is large, it's close to the cusp, then this is negligible and you get lambda to the 1/12th, which is like insanely better than the lambda to the quarter. So this is a feature. If you have these modular forms, when you go near the cusp, you beat the compact bound very well. Of course, if you are close, if y is small but bounded, then you get lambda to the quarter. So nothing better than your compact bound. So in compact sets, you get something like the compact bound, but when you go towards the cusp, you get something much better. And I want you to just, I'll remind you of this result later as well, but I want you to keep this in mind, because later when I talk about sup norms on these liftings, one of our first results will kind of look like this. So this is kind of a prototype. Why is this not as good as the holomorphic thing? Well, as you are well aware, if you're looking at Maass forms, then the Fourier expansion, first thing, the Fourier coefficients, we don't have the Ramanujan bound, and the Fourier expansion involves k Bessel functions, not exponentials. And k Bessel functions don't have as good convergence properties as exponential. So this is kind of what happens in the Maass forms case. The last result I want to mention is that of Blomer, and this is a very beautiful paper where he's looking at Ziegel cusp forms, so higher genus modular forms, and again he's using the Fourier expansion. But in this case, really, it's not possible, at least in this paper, it was not possible to do general Ziegel modular forms. So he's looking at lifts, which are Saito Kurokawa lifts and Ikeda lifts, which are given in terms of GL2 modular forms. So kind of the results we want to talk about, these last two results are, last two references are kind of the template or the motivation for what we started to do. And so what I want to do is now I want to give you the lifts that I'm talking about, and the one we worked out with Jinkun. I want to tell you how they are defined and how they are natural generalizations of Maass forms with respect to SL2, and how we can ask these relevant questions of sup norms for them. Okay, so this is my brief introduction to sup norm problem with a very sketchy history. If you are an expert in sup norms, then you know how incomplete this is. If you're not, then hopefully you got a flavor of what kind of stuff is going on in this part of mathematical world. Okay, so let us then go to these liftings. So these liftings will live on n+1 dimensional hyperbolic spaces. And the definition is very easy. Hn is x comma y, where x is in Rn and y is positive. And we have, of course, seen these guys earlier in the context of complex upper half plane. So H1 is exactly our complex upper half plane. And we know that the complex upper half plane can be realized as a symmetric space. So this is the group acting on it and the compact which you quotient out. And we can notice that our SL2R, there's an accidental isomorphism to the orthogonal group SO12. So this is kind of a prototype H1 written as orthogonal group modulo compact as a symmetric space is the prototype we want to construct for Hn. So we want to write Hn also as a symmetric space and then define Maass forms on this hyperbolic space as functions on the group. So what is the orthogonal group that is going to be acting on Hn? Well, the way you construct is the following. So given this integer n, we take a matrix S, which is a positive definite symmetric matrix. And this is an n by n matrix. And we put it into this n+2 by n+2 matrix and call it Q. So this is size n+2. And using the Q, you define the orthogonal group. So G transpose QG equals Q. And you can see the way S is chosen and the way Q is set up. If you look at the real points, then there is 1 plus and there are n+1 minuses. So this is signature 1 comma n+1. And this group, this real points of this group has a very nice Iwasawa decomposition. So the Iwasawa decomposition is given by the following. So there's a maximal compact K infinity. And the unipotent radical is parameterized by x in Rn. So this is the x in Rn that we see here. And it is this kind of a matrix right here. And the torus is parameterized by positive reals y, where you have y and a y inverse at the corners and the identity in the between. And so you can see that indeed you can identify our n+1 dimensional hyperbolic space with this symmetric space, taking the nx ay to x comma y. And this is exactly a generalization of your H1 situation. And I'll repeat this many, many times. Oh, you see, this is generalization of your usual mass forms. So this is a common theme. So our modular forms are going to live on the group G infinity. And so if you want to define modular forms, you have to define it with respect to some arithmetic subgroups. So how do you get these arithmetic subgroups? Well, most often you get it by taking them as stabilizer of lattices. So you can do that in this case as well. So you take any maximal lattice L in Qn with respect to your matrix S. You fatten it up to L0 because dimension n plus 2. And then your gamma S is the rational points in the group which stabilize your lattice. So this is your arithmetic group with respect to which you want to define the modular forms. And then now we can write down the definition. So the definition is you have smooth functions on your real group G infinity such that, well, you want it to be an eigenfunction of the Casimir. And I'm writing the eigenvalue in a specific way. It involves the size n and this real number r. And so it's an eigenfunction of the Casimir. Then on the right, it has invariance under k infinity. So indeed, it's a function on G infinity mod k infinity, which is your Hn. And on the left, it is invariant under your arithmetic group. That's how you define your mass forms. And you throw in a moderate growth condition. So these are the objects that we want to consider. And of course, with the arithmetic subgroup gamma S, there is a possibility of several cusps. And if you say that, well, I want your modular form to vanish at the cusps, then it's called a cusp form. And these cusp forms, if you work out with this Casimir and eigenfunction, it has a very nice Fourier expansion. So if you look at a cusp form, the Fourier expansion looks like this. So it's a big expression, but it's very easy to explain. So it's parameterized by non-zero elements of the dual lattice. So L is the lattice that you started with. L sharp is its dual. For every element in the dual lattice, you have a complex number, which is a Fourier coefficient. And then in the variable y, you have the k Bessel function with the power of y. And in the variable x, which is in Rn, you have an exponential function, e to the 2 pi I, with the character right here. And once again, this is a clear generalization of what you see for Fourier expansions of mass forms. So if you have a mass form with respect to SL to Z, then you can write out its Fourier expansion in terms of the Whittaker function or the K Bessel. So you can see this expression right here is corresponding to the Fourier expansion that we have up here as well. So moral of the story is that these mass forms on these n+1 dimensional hyperbolic spaces are natural generalizations of mass forms that we have seen on complex upper half plane. So what we're going to do is we're going to not consider the whole space of these mass forms, but certain subspace, which is coming from lifting from mass forms on GL2. But before we do that, to make our life a little simpler, we are going to make an assumption on the lattice L. Namely, we're going to assume that L is a unimodular even lattice. And that does two things for us. The important thing is that the dual is same as L, which means the lattice has no level. There's no level of modular forms that you have to deal with. So this is a very convenient thing. And of course, these unimodular even lattices only exist when the size n is divisible by 8. That is why in the title you saw O1 8n+1. So the capital N was replaced by 8n+1. That was a reason for that. And there are lots of examples of these unimodular even lattices. For example, in dimension 8, you have the E8 lattice. In higher dimensions, you have multiple copies of E8 or other kinds of unimodular even lattices. So there are enough examples out there. And so you fix this lattice. And now what you do is you start with a mass form on SL2Z given by this Fourier expansion. I'm taking the Fourier expansion with respect to this Whittaker function here. And then using these Cn's, I'm going to give you a formula for A lambda. So for every non-zero element of L, see L sharp is the same as L, so I can just take L. I'm going to define A lambda in the following way. I take all divisors D of D lambda, where D lambda is essentially the GCD of the components of lambda. And then I'm going to go to the Fourier coefficient of the Maass form on GL2 and evaluate it at a number which corresponds to the norm of lambda divided by d squared, and then interpolate it with the power of d. So this is a very explicit formula. If you know your C's, you know your A lambdas. And if you have had the opportunity to see Saito Kurokawa lifts in your studies, then you will recognize that this is a very similar formula to the formula for Fourier coefficients of Saito Kurokawa lifts. So that is kind of the motivation here as well, the connection to Saito Kurokawa lifts and the connection to these Maass forms right here. So I started with F, I gave a formula for A lambda, and then I set up this function on G infinity as a Fourier expansion where things are, the Fourier coefficients A lambda are defined in this way. So what is this function capital F sub F? Well, it certainly is taken to be right invariant under K infinity. So that property is done. The Fourier expansion tells me two things. First is that it's eigenfunction of the Casimir. That's how the Fourier coefficients expansion is built, and that it has moderate growth. So the only thing that is missing is left invariant under the discrete subgroup. So if you can get that, then this is the example of a Maass form on the n+1 dimensional hyperbolic space. So we explicitly give a description, and then we hope to show modularity. And this was the content of the paper with Yinkun and Hiroaki Narita. And so I want to give you a brief synopsis of the result from that paper. So that's on the next slide. So let us see. So the first thing is that indeed this map from little f to capital F sub f takes Maass forms on SL2 to the Maass forms on our n+1 dimensional hyperbolic space. Not only that, it takes cusp forms to cusp forms and Hecke eigenforms to Hecke eigenform. So the nicest kind of map that you can expect. All properties are being satisfied. And then natural question is, how did we do this? How did we show the modularity with respect to this gamma s? The point is, it's almost impossible to show it directly because gamma s does not have nice, easy generators. It's quite complicated and so on. So you do it in a completely roundabout way. And this was Yinkun's idea, and we followed this and we were able to do it. So the idea is to look at Borchard's theta lifts. So in a 1999 paper, Borchard did this amazing paper on theta lifts where he started with a wide range of input functions, different Maass forms, meromorphic functions, and whatever you want, you put it in. And he had an explicit description of the theta kernel, and he did the theta lift to give you modular forms on various orthogonal groups. So when you do the theta lift, that is, if you know anything about theta lifts, this is the main thing. Whenever you do a theta lift, the automorphy is free. It's in part of the construction. So if you start with an F here and you do its Borchard's lift, the automorphy is free. The amazing thing about Borchard's paper is that he also says, oh, I'm doing everything classically, and I'll tell you how to find the Fourier expansion of the lift. So I'll give you a recipe of how to do it. So Yinkun, me, and Hiroaki, we follow Borchard stuff, and we find out what the Fourier expansion of Borchard's theta lifts look like. And probably you can guess now. Borchard's theta lift Fourier expansion exactly look like this thing with this formula of AF lambda. So this is how we get automorphy of our lift, by realizing it as a Borchard's theta lift. So this is an important feature of this result, and we'll be using it again for future steps. So we have a Maass form now. Cusp forms go to cusp forms. Hecke eigenforms go to Hecke eigenforms. So if you do start with the Hecke eigenform F, Capital F is a Hecke eigenform as well, and you can form a representation of the adelic points of the group. So these are irreducible cuspidal automorphic representations. And at every finite place, these are actually spherical. So there is no level here. So they are spherical constituents of the unramified principal series. And all of these constructions being so explicit, we can actually write down the Hecke eigenvalues of capital F in terms of the Hecke eigenvalues of little f. And that way we can write down explicitly the Sataki parameters of all of these guys. And these are encapsulated in the following formula for the L function of the lift. So the L function of the lift, it's an n+2 degree L function. It has a degree 3 part, which is a symmetric square L function of your Maass form that you started with, and then a big bunch of zeta functions which are shifted. So it's a very nice description of the Sataki parameters. And you can see because of the shifts in the zeta function, these Sataki parameters don't have absolute value 1, which means they violate Ramanujan. So this was one of the motivations that me and Yinkun and Hiroaki had to do these constructions to obtain examples of modular forms which do not satisfy the generalized Ramanujan conjecture. So indeed, for p less than infinity, they are non-tempered. So that's the representation theory way of saying it violates Ramanujan. At the Archimedean place, it is tempered indeed. So this is the story of the lift, and the story coming from paper with Yinkun and Hiroaki. And beyond this is something I think even new to Yinkun. So before I go on, are there any questions? Do you have any questions on whatever I was saying so far? One thing you could ask, which does not seem to be in this theorem, is, oh, is this map, is this lift non-zero? And if you know theta lifts again, then you know that if you construct theta lifts, automorphy is free, but non-vanishing often is extremely complicated. But we have an advantage here in the sense that we have a very explicit formula for this A of lambdas. So you might think, well, you know that there are several coefficients of the Maass forms C's which are non-zero. So if you can find elements lambda in the lattice such that when you plug in their norm here, the relevant coefficient of C is non-zero, then you get non-zero Fourier coefficient, so non-zero lift. And that works very well if indeed your lattice L, the norm map is, for example, surjective. So for example, if your lattice is a copy of multiple copies of E8, then the norm map is surjective, and then you get all possible coefficients here. So because you see, when you have a Maass form on GL2, you know that some Fourier coefficient is non-zero. How do you know which one? So you don't know which argument to put in here. But if your norm map is surjective, then you got all of them. So non-vanishing of C implies non-vanishing of A. But what if you have lattices which don't have a surjective norm map? So the way we worked around it, Yinkun and Hiroaki, we said, oh, if your lattice does not have a surjective norm map, why don't you look at Fourier coefficients at different cusps? And if you go around all the cusps, the lattice changes every time, but it turns out that in this orbit of your lattice, you get all of them, which means you also get a copy of E8. So somehow, maybe the Fourier expansion you started with does not give you what you want, but going at different cusps does make it work. So indeed, this map is an injective map. So we were able to get that as well. Another way to see this injectivity, which is more traditional way for theta lifts, was an idea of Rallis. Rallis did a lot of work on theta lifts in the 70s and 80s. And he said, well, if I want to know that my theta lift is non-zero, one of the ideas is to get a formula which relates the L2 norm of the lift in terms of the L2 norm of the function you started with. So if you can say that this guy is a non-zero constant times this guy, then you got your injectivity of the map. So me and Hiroaki, we started thinking about the L2 norm of capital F. You see, another motivation for looking at L2 norm, if you remember my examples from sup-norm things in the earlier slide, there was always the L2 norm in the denominator. So if you want to say anything about sup-norms, we need to know something about the L2 norm. So we were investigating the L2 norm for this reason. And so we start with Hecke eigenform. You have the capital F, which is a Hecke eigenform as well. We idealize it. There is a idealization procedure for Borchert's theta lift due to Steve Kudla, for example. And then we can throw this into the Rales inner product machinery. And I'm not giving you all the details, but I'm telling you one key thing that comes up from the Rales inner product. You can write the square of your L2 norm as a double integral right here. So this looks big and complicated, but actually it's not so difficult to understand. So what's happening here is that this F0 is just the idealization of your F. So this is your GL2 modular form or an SL2A. So this is two copies of this in variable G1 and G2. The E here is an Eisenstein series, and this is an Eisenstein series on sp4, the symplectic group of genus 2. And this is constructed using a function here, which relates to the Borchert's theta left. So Borchert's theta left tells you what this input is, which tells you what the Eisenstein series is. And then what do? You take the Eisenstein series on sp4, and inside sp4, you can embed two copies of SL2. So you take this Eisenstein series, restrict to two copies of SL2, and in each variable, you integrate it against F0 and F0 bar. So that's what this integral is. Eisenstein series on a bigger group, restricted to two copies of SL2, and then integrated this way. So this is a natural thing which comes out of Rales inner product machinery. And then Rales tells us that this big integral, it's over SL2A mod SL2Q2 copies, is actually Eulerian, which means it can be written as a product over all places, and then there are local integrals. And these local integrals involve matrix coefficients of F and so on. And indeed, for the finite places, you can use the machinery of Rales, or Boscher has worked on it, and you can compute them explicitly. The only thing which is not available is the Archimedean computation. And me and Hiroaki, we tried the Archimedean computation using the matrix coefficient, but we were unsuccessful. And these things are usually very hard. The Archimedean computations are very hard. I should mention that in a slightly different Borchert's theta lift, where you start with holomorphic F and construct the theta lift to signature 2, n, Jan Brunier, who's in the audience, and Jens Funke, they have actually computed this L2 norm of the lift. And actually their paper was very helpful to us. I wrote several emails to Jens trying to understand his paper. He was very helpful. So hopefully Jan will appreciate the complexity of the Archimedean computation. So we want to do the Archimedean computation. So we said, okay, let us look at this integral in a slightly different way. Let us look at just this inner integral. So I'm calling it capital Z. And this is a function of G2. And it turns out, so we have worked on these kinds of integral earlier, me and Ralph Schmidt and Abhishek Saha. And it turns out that this inner integral is also Eulerian. So it's a product over all places and some local integrals. And these local integrals, again, at the finite places can be explicitly computed. And they are very nice expression. So this is the degree 3 L function of the GL2 representation and two zeta factors in the denominator. And your function FP shows up right here. So it's a constant times your FP. The Archimedean thing is the one which me and Hiroaki started computing, and I am actually not going to give you the details of that computation here, but I'm going to tell you what the answer is. So the answer is the following. So maybe I go back to the slide once again. So the answer in this case is that the Archimedean integral is a constant times f infinity. So f infinity together with all of these fp's gives you the f0. So what does it give you? This inner integral is a constant times f0 of g2. So you pull the constant out and you get an integral over SL2 of f0 g2 and f0 g2 bar, which is the L2 norm of f0. So L2 norm of f shows up and a big constant in the front, where this part comes from the non-Archimedean computation, and the Archimedean computation gives you a bunch of gamma factors. The gamma factors depend on the dimension n and the Laplace or the Casimir eigenvalue r. So very nice explicit formula. You can check that all of this is non-zero, giving you a new proof of injectivity of this map. Okay. So now what do we have? We have two things. We have, for these lifts, we have an explicit formula for the Fourier coefficients in terms of Fourier coefficients of GL2 mass forms. We have an explicit formula for the L2 norm, and these are the two ingredients which go into the Fourier expansion method for sup-norm problem, which I mentioned in the earlier slides. So we put all of this thing into the Fourier expansion method, and I'm going to actually just start with the first result we have. And this is joint work with Simon Marshall and Hiroaki. So the history is very nice. Me and Hiroaki were doing this first. And if you know either of us, we have little to no expertise in analytic number theory. We were still doing these applications. And at some point, Simon contacted us and said, oh, you can do this, you can do that. And I'll tell you more interesting part of the story is towards the end. It turned out that he was able to enhance our results a lot. And of course, we invited him to be a co-author in our paper. So this is the first result, which says that the absolute value of the function divided by the L2 norm is bounded above by exponent of r and bounded below as well. And the exponent of r involves the size n of the dimension. The theta here that shows up is the bound towards Ramanujan that you know for mass forms on GL2. So when one of you guys proves Ramanujan for mass forms, I can make this theta equal 0. I have written it in a form where I have still kept this y in the denominator. And let me remind you, Templier's result was exactly with this y in the denominator here. So this is a prototype of what Templier got for the GL2 mass forms. And so once again, I'll give you a brief idea of how to prove this thing. But once again, just to look at the result, when y goes to infinity, this term becomes negligible and you get r to the n by 4. So this is the kind of bound you get when you go to the cusp at infinity. If you stay in y compact, then this is the term which dominates. So it's r to the 3n by 4, which is much worse than what you are getting at the cusps, which is exactly the story in Templier's result as well. So this is our first result. So this is using the Fourier expansion method. So how does this work? Let me maybe so before going into maybe some of the details of the proof, maybe I can pause again and see if you have any questions about the L2 norm thing or this one. Okay, you can hold your questions till the end too, or if you don't have questions, that's fine as well. So let us see what is going on. So I want to show a result of this kind. So basically, you take this expression and you replace the numerator by its Fourier expansion. You use Cauchy-Schwarz, and then the exponential part goes away because it was e to the 2 pi I something, so that goes away. And so you have this thing on the right-hand side, which you need to bound. So you need bounds on the k-Bessel function, and you need bounds on the a lambda with the L2 norm here. So need estimates on this. Now we know that this A lambda is defined using the Fourier coefficients C of little f. So what we do is we do this obvious thing, you multiply by L2 norm of f and divide by L2 norm of f. And the reason for doing that is that already we have a theorem which gives an explicit formula for this guy. This is going to be in terms of those L values and gamma functions that we wrote down earlier. And for this guy, what do you do with this one? Again, so the important point is explicit formula for L2 norm of f takes care of this expression, and the explicit formula for A lambda takes care of this expression. So how does it do that? Okay, so this is the first part for the L2 norm. And the second one for Fourier expansion, well, you plug in the Fourier expansion, the C's show up here, and since you have assumed that it's a Hecke eigenform, you can pull the C1 out and you get the Hecke eigenvalue. So the Hecke eigenvalue here contributes the theta term, and the first Fourier coefficient divided by its L2 norm. There's a very deep theorem of Hofstein and Lockhart, which gives you a bound for this term for L2 for GL2 mass forms. So knowing the A lambda in terms of the little f is crucial to obtain a bound for this term. So this is the reason why if you took random mass forms on n+1 dimensional hyperbolic space, we won't be able to figure out what to do with this term here. We may have general bounds on Fourier coefficients of Cuss form, but they're not going to be too good. And so that is the reason to restrict ourselves to these lifts, because we have so much more information, so much more explicit information. Okay, so the Peterson norm gives us some power of r. This is a power saving with the exponential. This one gives you this exponential as well. So if you put together both of these exponential with the k Bessel, then there is the bounds on the k Bessel function. So the k Bessel function works the following. There is a crucial value of the argument beyond which there is exponential decay, and before which there is just a polynomial thing. So the whole thing here, the bounds hinge on how well do you understand the asymptotics of the k Bessel function. So the result that I have mentioned here is using this kind of asymptotics. Later, Simon Marshall was able to obtain better asymptotics than this. So if you look at the paper version of this result, you have finer bounds than this one. So essentially, you plug in all of these, and then you look at how many elements in the lattice have a particular norm. You can estimate these using actually results from Serre's book, Course in Arithmetic, and all of that put together does give you a bound of this kind. So I actually haven't showed you the nitty-gritties of the proof, but I have told you the three main ingredients: the bounds on the L2 norm, the bounds on Fourier coefficient, and the bounds of the k Bessel function, which is what is going on in this Fourier expansion. So if you have these three in your favorite modular form, you can write down a theorem on sup-norms. So this is kind of a template that is there. So this is one of the results using Fourier expansion method. And this is exactly what me and Hiroaki were doing. And this is where we ended our paper. And then we actually even put it on the archives, I think. No, actually, maybe we just sent it to Simon and so on. And then Simon said, you know, there is another very standard technique for sup-norms. It's called the pre-trace formula method. And that actually would give similar results to what you have, but that is applicable to all mass forms. You don't have to restrict to lifts. So let me just write it down for you guys, and we can add it as an appendix or something. So the pre-trace formula method says, and this is very general, it says that if you have any finite volume hyperbolic orbifold of dimension n+1, and you take a L2 normalized eigenfunction of the Laplacian, then there is an upper bound here. Okay, and in our context, in our specific context, this upper bound gives you expression of this kind. And there's a crucial difference between this one and the previous bound, namely y is in the numerator, which is going to tell us that when y goes off to the cusp, this is not going to give me anything good because this is going to blow up. But when y is very small, this is probably going to give you a better bound than the Fourier expansion method. So this was the idea right here. And so the point is that for small values of y, the pre-trace formula method gives you r to the n by 2, but it really sucks at large values of y. And the Fourier expansion method for large values of y, it gives you r to the n by 4, which is very good. But for small values of y, it really is bad. So in the y variable, large values, Fourier expansion method is good, or small values, the pre-trace formula method is good. Over the whole range of y, both of them are okay. So what if we can put it together and the parts where both the methods are really good are exactly complementary, then we got a better theorem than we could get by individual methods by themselves. So that was the crucial observation by Simon, and I want to show that to you right here. So this is a very satisfying slide because you'll see why. So the pre-trace formula method gives us something like this. The Fourier expansion method gives us something like this. And I want to look at different ranges of y, and I want to see which method is better than the other. So if your y is bigger than r, then if you look at this one right here, it is overshadowed by r to the n by 4. So you get r to the n by 4 bound. But of course, y bigger than r gives you really a bad bound in the pre-trace formula method, which is what I said. Large values of y, Fourier expansion method, great. Pre-trace formula method, not so good. In fact, not just y bigger than r, if you go further below to square root r. So if y is bigger than square root r, this thing is going to start contributing. But you can see if y is square root r, this cancels out to give you r to the n by 2. So not as good as r to the n by 4, but still r to the n by 2, which is better than r to the 3n by 4, which shows up right here with y square root r and r. So even when you go a little closer up to square root r, the Fourier expansion method is still better than the pre-trace formula, but not as good as in the large y range. Okay, how about y smaller than square root r? Well, if y is smaller than square root r, you can see that this is r to the n by 2, r to the n by 2, so we get r to the n by 2, whereas the Fourier expansion method gives you r to the 3n by 4. So the magic, of course, is that this square root r is the common point to the right of which the Fourier expansion method gives you r to the n by 2, to the left of which the pre-trace formula method gives you r to the n by 2. So together, they give a much better bound than the r to the 3n by 4 that the individual methods have. So that is our final theorem. And this is the reason why Simon Marshall is not just writing an appendix to our paper, but he's a co-author, because each method by itself gives you something, but not as good as in certain subsets. But these subsets are exactly complementary. So together, they provide a much better result. So this is the final formula here, and I want to stop at this point. Thank you very much.